Welcome to DREAMLAB Knowledge, where we explore the profound mysteries of science, nature, and our changing world through calm, contemplative storytelling. Tonight, we journey to the far north, to Earth's frozen frontier, where climate change is rewriting the ancient rules of snow and ice in ways both fascinating and terrifying. How climate change is supercharging Arctic avalanches. Picture, if you will, a mountain slope in the high Arctic. The landscape appears frozen in time, a realm of eternal winter where ice and snow have held dominion for millennia. But beneath this seemingly unchanging surface, something fundamental is shifting. The ground itself is betraying its ancient architecture, and the snow that has settled season after season for thousands of years is beginning to behave in ways that defy centuries of accumulated wisdom. This is the story of how climate change is rewriting the rules of one of nature's most powerful forces. It's a story about avalanches in the Arctic, about communities learning that historical experience no longer provides a reliable guide to the future, and about a frozen world that is quite literally coming apart at the seams. It's a story that begins not with the dramatic rush of cascading snow, but with something far more subtle, a single raindrop falling where rain should not fall. The Arctic that was to understand what's changing, we must first understand what the Arctic once was. For most of human history, the Arctic represented the planet's most stable frozen realm. The region's climate operated within predictable boundaries. Winters were long, dark, and brutally cold. Summers were brief, with the sun never quite warming things enough to melt the permafrost that lay beneath the surface. Snow fell, accumulated, and stayed put for months, building up in predictable patterns that communities learned to read and respect. The traditional Arctic snowpack was a marvel of crystalline engineering. Each layer told a story, a frozen record of the winter's weather patterns. When snow fell in these extreme latitudes, it arrived dry and cold, the flakes light and feathery, unable to hold much moisture in air that seldom rose above freezing. These dry snow crystals would settle onto slopes, layer upon layer, creating a snowpack that was stable, predictable, and relatively benign in its behavior. The cold temperatures meant that once snow fell, it remained frozen solid until the brief summer thaw. Avalanches certainly occurred in this older Arctic climate, but they followed patterns that locals came to understand. They happened after major snowstorms, when the weight of fresh accumulation exceeded the strength of the layers beneath. They occurred on steep slopes where the angle overcame the friction holding the snow in place. They were dangerous, certainly, but they were predictable dangers, ones that experience and caution could help navigate. The communities that made their homes in these harsh environments developed sophisticated knowledge systems for reading the snow. Indigenous peoples of the Arctic, from the Sami reindeer herders of Scandinavia to the Inuit of North America, built vocabularies for snow and ice that numbered dozens or even hundreds of terms, each describing specific conditions, specific dangers, specific opportunities. This knowledge, accumulated over generations, formed the foundation of survival in a landscape that offered no second chances for mistakes. But climate change is rendering this accumulated wisdom increasingly obsolete. The Arctic that exists today is not the Arctic of even 30 years ago, and the avalanches that now threaten Arctic communities are creatures of a new and unstable climate regime. The warming edge of the world. The Arctic is warming faster than any other region on Earth. This isn't speculation or projection, it's measurable fact, written in temperature records, visible in satellite imagery, felt by every person who calls the far north home. Since 1979, the Arctic has warmed at a rate nearly 4 times faster than the global average. In some specific locations, winter temperatures have risen by more than 3 degrees Celsius in just a few decades. This phenomenon, known as Arctic amplification, occurs because of a series of self-reinforcing feedback loops. As sea ice melts, it exposes darker ocean water, which absorbs more solar radiation than reflective ice. As permafrost thaws, it releases methane, a potent greenhouse gas. As snow cover diminishes, the land beneath absorbs more heat. Each of these changes accelerates the others, driving the Arctic into a new climatic state at breathtaking speed. The consequences of this warming touch every aspect of the Arctic system, but few are as immediately dangerous as the changes occurring in snow and ice dynamics. The warming Arctic isn't simply experiencing less snow, it's experiencing different snow, falling at different times, accumulating in different ways, and behaving according to rules that no one has quite figured out yet. In Svalbard, the Norwegian archipelago that sits between mainland Norway and the North Pole, researchers have documented something that would have seemed impossible just decades ago. In February of 2025, the temperature at Ny-Ålesund, the world's northernmost permanent settlement, averaged -3.3 degrees Celsius. This might still sound cold to those of us from temperate latitudes, but it represents a staggering departure from the historical average for that month, -15 degrees. For 14 days out of 28, temperatures rose above freezing in February. In the high Arctic, these warm spells aren't anomalies anymore. They're becoming the new normal. And with them comes something the traditional Arctic rarely experienced: rain falling on snow, the deadly kiss of rain on snow. Rain on snow, three simple words that have become a phrase of dread in Arctic communities. When rain falls on a snowpack, it triggers a cascade of physical and chemical changes that fundamentally alter the snow's structure and stability. Water percolates through the layers, melting bonds between crystals, adding weight, lubricating interfaces, and creating conditions for catastrophic failure. In a cold, dry snowpack, individual snow crystals bond together through a process called sintering. The points where crystals touch develop necks of ice that grow stronger over time, creating a coherent mass. But when liquid water enters this system, everything changes. Water dissolves these bonds at the molecular level, breaking the connections that hold the snowpack together. The snow becomes heavy, waterlogged, and unstable. The process unfolds with terrifying speed. Rain can transform a stable snowpack into an avalanche-prone death trap in a matter of hours. The water adds weight to the surface layers, loading them onto weaker layers beneath. It acts as a lubricant at layer interfaces, reducing friction. And perhaps most dangerously, it can pool at impermeable layers within the snowpack, creating zones of weakness that can suddenly fail. When the rain stops and temperatures drop again, the water-soaked snow freezes into solid ice. This creates ice crusts and layers that pose different but equally serious problems. These ice layers prevent animals like reindeer and caribou from accessing the vegetation beneath the snow. They alter the insulating properties of the snowpack, affecting permafrost beneath, and they create weak interfaces for future avalanches. The Arctic is experiencing more rain-on-snow events than ever documented in the historical record. In parts of Alaska, rainfall has increased by 17% over the past half-century. In Svalbard, winter rain events that were once rare enough to be noteworthy are becoming routine. Climate models project that Arctic rainfall could increase by 40% or more in the coming decades. Each rain-on-snow event is a potential trigger for what researchers call wet avalanches, a category of snowslides that behaves very differently from the dry powder avalanches more common in temperate mountain ranges. Wet avalanches are denser, slower, and far more destructive. They carry more mass, exert greater forces, and flow like viscous liquids, rather than tumbling like dry powder. When they hit structures, they don't just knock them down, they crush them, flatten them, and bury them under tons of solidified concrete like snow. The slush that kills. But rain on snow creates an even more dangerous phenomenon that's almost unique to Arctic and subarctic environments: Slush avalanches, sometimes called slush flows. These are not avalanches in the traditional sense. They're something else entirely, something that combines the worst characteristics of avalanches, mudslides, and flash floods into a single catastrophic event. A slush avalanche begins when rain or rapid melting saturates a snowpack beyond its capacity to hold water. Unlike dry avalanches, which require slopes of 30 to 45 degrees to initiate, slush avalanches can start on slopes as gentle as 10 or 15 degrees, places where conventional avalanche theory says snow should be perfectly stable. The water-saturated snow becomes a heavy slurry that begins to flow, picking up speed and mass as it descends. What makes slush avalanches so terrifying is their energy. A typical slush avalanche can reach speeds of 60 to 100 kilometers per hour, but it carries far more mass per unit volume than a dry avalanche. The mixture of water and snow gives it the consistency of wet concrete. It flows further, travels faster, and hits harder than almost any other type of avalanche. It can travel across flat terrain where dry avalanches would stop. It can change direction following drainage channels and valley bottoms, and it's almost impossible to predict. In Norway's far northern Finnmark County, authorities have documented 55 slush avalanche events, several of them fatal. But researchers suspect this number represents a dramatic undercount. Until recently, slush avalanches weren't well understood, weren't distinguished from regular avalanches in incident reports, and weren't being systematically studied. As awareness has grown, so has the apparent frequency of these events, though it's unclear how much of this increase reflects better reporting versus actual changes in occurrence. What is clear is that slush avalanches pose a growing threat to Arctic infrastructure and communities. In Svalbard, slush avalanches have destroyed bridges, closed roads for days, and crossed heavily traveled snowmobile routes. In 2010 and 2011, extreme midwinter slush and wet avalanche cycles produce slides of unprecedented size and run-out distance, threatening settlements and infrastructure across the archipelago. Analysis of meteorological records from Longyearbyen, Svalbard's largest settlement, reveals a troubling pattern. Between 1912 and 2011, only 4 large-scale slush avalanche periods were identified in the record. 3 of them occurred in the 1990s. The frequency and intensity of these events appears to be increasing in lockstep with warming temperatures and increased winter precipitation. Researchers studying slush avalanches face a fundamental challenge. There's no reliable way to predict them. Traditional avalanche forecasting tools developed for dry snow avalanches in more temperate mountain ranges don't work for slush flows. The trigger mechanisms are different. The terrain involved is different. The entire physics of the phenomenon operates according to different rules. Scientists are racing to develop predictive models and early warning systems, but the task is complicated by the rapid pace of climate change itself. The historical record that normally formed the basis for hazard assessment is becoming less and less relevant. When the mountains come apart. While rain transforms the behavior of snow, rising temperatures are attacking the Arctic landscape from another direction entirely: the ground itself. Permafrost, the permanently frozen ground that underlies much of the Arctic, is thawing at unprecedented rates. And as it thaws, it's destabilizing mountain slopes in ways that are triggering a new generation of deadly mass movements. Permafrost isn't just frozen soil. In many Arctic regions, it's the glue holding entire mountains together. In the cracks and crevices between rocks, ice accumulates over millennia, filling voids, cementing loose material, and creating a solid matrix that stabilizes even the steepest slopes. This mountain permafrost can extend hundreds of meters into bedrock, creating what's essentially a frozen mountain. But as the Arctic warms, this ice is melting. Water is extraordinary in its properties as a solid versus a liquid. When it freezes, it expands. When it melts, it contracts. The ice that once held rocks together disappears, leaving voids and weaknesses. Water seeps into these gaps, freezes and thaws cyclically, wedging rocks apart. The entire mechanical structure of the mountain is being undermined from within. The results are catastrophic. Rock avalanches in the Arctic are increasing in both frequency and magnitude. In Alaska's Glacier Bay National Park, researchers analyzed 33 years of satellite imagery and identified 24 rock avalanches. These weren't small rockfalls. These were massive slope failures involving millions of tons of rock, some of them creating tsunamis when they crashed into fjords and glacial lakes. The pattern of these rock avalanches tells a revealing story. 75% of them occurred on north-facing to northeast-facing slopes, the aspects where mountain permafrost is most abundant and where warming is having the greatest effect. They clustered in time, appearing in pulses during periods when freezing levels rose above their historical averages for multiple consecutive years, and they initiated at increasingly high elevations, suggesting that warming is progressing up the mountains, thawing permafrost at altitudes that were once permanently frozen. In October 2015, a rock avalanche on the Tyndall Glacier in southeast Alaska became the largest non-volcanic landslide ever recorded in North America. Approximately 180 million tons of rock detached from a mountainside and cascaded down onto the glacier. The impact generated a tsunami that ran up the opposite shoreline to a height of 600 feet, one of the largest tsunami run-ups ever documented. Had this occurred in a more populated area, the death toll would have been catastrophic. Svalbard is experiencing similar destabilization. Retrogressive thaw slumps, landslides triggered by permafrost degradation, are appearing across the archipelago. Researchers have documented thousands of these features, their scarred surfaces visible in aerial photographs, their unstable headwalls continuing to retreat year by year. The Norwegian government has begun systematic mapping of permafrost hazards, creating inventories of thaw slumps and thermo-erosion gullies, phenomena that were once rare but are now becoming commonplace across the Arctic landscape. The economic implications are staggering. In Alaska alone, projections suggest that building and road damage from permafrost thaw could cost between $37 and $51 billion by mid-century. Infrastructure built on the assumption of permanently frozen ground is sinking, tilting, and collapsing. Water systems are failing as the frozen ground they were built on turns to mud. Buildings are becoming uninhabitable, and in steep terrain, the thawing permafrost is creating conditions for avalanches on a scale never before witnessed in these regions. December 19, 2015. To understand what all these changes mean in human terms, we need to travel to a specific place at a specific moment in time. The place is Longyearbyen, Svalbard. The moment is the early morning hours of Saturday, December 19, 2015. Longyearbyen sits in a valley on Spitsbergen, the largest island in the Svalbard archipelago. It's the world's northernmost permanent settlement, with more than 1,000 inhabitants. A mining town turned tourism and research hub, home to about 2,000 people from more than 50 nations. The town sprawls along the valley floor, colorful wooden houses climbing partway up the surrounding slopes. Above the town looms Sukkertoppen Mountain, its slopes rising steeply from the settlement's edge. For decades, Longyearbyen had existed in an uneasy truce with the mountain. Avalanches happened, certainly. Historical records documented slides in 1917, 1949, 1953, and 1979. But these were rare events, separated by decades, and they hadn't hit the inhabited parts of town. The risk was acknowledged but considered manageable. On the night of December 18th, A powerful storm system moved into the region. Winds gusted to gale force. The temperature hovered around freezing, warm by Arctic December standards, and it began to rain. Not snow, rain. Liquid water falling from the sky in December in the high Arctic. The rain fell through the night, saturating the snowpack that had accumulated on sucker-topping slopes. Somewhere high on the mountain, in the pre-dawn darkness, the snow reached its breaking point. A slab fractured, and approximately 100,000 cubic meters of wet, heavy snow began to move. The avalanche reached the inhabited area at approximately 7:25 in the morning. Most residents were still sleeping. The wall of snow and ice, moving at tremendous speed, struck a row of apartment buildings at the foot of the mountain. The force was unimaginable. 11 houses were displaced from their foundations and totally destroyed. More than 20 people were trapped inside demolished buildings. 9 were buried in the snow, some for nearly 2 hours. Emergency services responded immediately, but the scale of the disaster overwhelmed local resources. More than 200 people were evacuated. The local hospital, itself threatened by the avalanche debris field, treated the injured. Rescue teams worked in darkness and continuing harsh weather, knowing that more avalanches could occur at any moment. When dawn finally came and rescuers could assess the full extent of the disaster, the toll became clear. 2 people were dead, a young woman and a 2-year-old child. Many others were injured. The physical destruction was immense, but the psychological impact was perhaps even greater. The avalanche had occurred in a zone that hazard maps had marked as safe. It had traveled further than historical models suggested was possible. It had happened in conditions that the old rules said shouldn't produce avalanches. In the aftermath, the Norwegian government launched intensive investigations. Expert panels convened. Hazard maps were redrawn. An avalanche warning system was established. Physical barriers were planned. The community began a difficult reckoning with a fundamental truth. Historical experience could no longer be trusted as a guide to future risk. But the worst was not over. Lessons unlearned. The avalanche warning system established after the 2015 disaster began operations in early 2016. It used meteorological data, snowpack monitoring, and expert analysis to forecast avalanche danger and trigger evacuations when necessary. The system was state-of-the-art, incorporating lessons learned from avalanche forecasting in other regions and adapted for Arctic conditions. On February 1, 2017, just 14 months after the first disaster, the warning system detected elevated avalanche risk. Authorities ordered evacuations of the most at-risk buildings. Many residents complied, but the avalanche that came did not strike where the models predicted. At approximately 9 in the morning, a second massive slide came down Suckertoppen Mountain. It followed a slightly different path than the 2015 avalanche, striking an area that included buildings that hadn't been evacuated. 2 apartment buildings were hit. While there were no fatalities this time, the damage was severe and the message was clear. Even with advanced warning systems and expert forecasting, avalanches in the rapidly changing Arctic had become fundamentally unpredictable. The 2017 avalanche demolished any remaining confidence in the ability to assess risk based on historical patterns. Analysis showed that the slide reached places that shouldn't have been reachable according to the models. It occurred under conditions that the forecasting system had deemed dangerous but not extreme, and it demonstrated that even extensive mitigation efforts might not be sufficient to protect communities from avalanches supercharged by climate change. The response to the second avalanche was swift and expensive. Massive snow fences were constructed on the mountain slopes above town, physical barriers designed to prevent snow from accumulating in the most dangerous starting zones. Supporting structures and drainage canals were built. Plans were drawn up for further mitigation work. The cost ran into the hundreds of millions of kroner. But here's the uncomfortable truth that researchers, government officials, and residents all had to confront. No one knows if these measures will be sufficient. Climate change is altering avalanche behavior faster than our understanding can keep pace. The protective structures were designed based on models of how avalanches behave, but those models are derived from historical data that may no longer apply. Studies of the Longyearbyen avalanches revealed something deeply troubling for avalanche professionals worldwide. The run-out distances of both slides were far greater than traditional avalanche models predicted. The alpha angle, a measure of how far an avalanche travels relative to how high it starts, was much lower than expected. In the 2015 avalanche, this angle was 26 degrees. In the 2017 event, it was 25 degrees. Conventional models for Norwegian avalanches suggest angles of 30 to 35 degrees. What this means in practical terms is that the avalanches traveled much further than they should have, and the explanation appears to lie in the wet, dense nature of the snow involved. The rain-on-snow conditions created avalanches that flowed more like fluids than like the dry powder avalanches that formed the basis for predictive models. They carried more momentum, lost less energy to friction, and behaved in ways that no one had anticipated. Shifting snow, shifting seasons. The transformation of Arctic avalanche patterns extends beyond isolated dramatic events. Across the entire Arctic region, researchers are documenting systematic changes in when, where, and how avalanches occur. Traditional Arctic avalanches followed predictable seasonal patterns. They happened primarily in spring, when increasing temperatures and solar radiation destabilized the winter snowpack. They occurred after major storms when heavy snowfall overloaded slopes. They initiated in specific terrain types on slopes between 30 and 45 degrees, and they traveled predictable distances based on the starting zone elevation and terrain features. Climate change is disrupting all of these patterns. Avalanches are happening earlier in the season, triggered by midwinter warm spells that would have been unthinkable in the climate of the past. They're happening in midsummer, when slopes that have been snow-free for generations are accumulating new snowpack from altered precipitation patterns. They're happening on gentler slopes, where water saturation allows snow to flow at angles that should be stable. Perhaps most significantly, avalanche activity is migrating upslope. As lower elevations warm and snow cover becomes intermittent, the zone of reliable deep snowpack is contracting toward the highest peaks. In the Vosges Mountains on the border of France and Germany, researchers documented this upslope migration through an extraordinary multi-century analysis. Between the late Little Ice Age and the early 20th century, as temperatures warmed by about 1.35 degrees Celsius, the annual number of avalanches decreased more than sevenfold at low and medium elevations. The avalanches didn't disappear. They moved uphill, retreating to the highest elevations where snow still accumulated reliably. This same pattern is now appearing across Arctic regions. Lower elevation avalanche paths are becoming less active or going dormant entirely as snow cover diminishes. But at higher elevations, above the rapidly rising freezing line, conditions are becoming more dangerous. Warmer temperatures mean that storms that once would have deposited dry, stable snow are now dropping wet, unstable snow. Increased atmospheric moisture means larger storm totals. Temperature fluctuations mean more freeze-thaw cycles, creating the dangerous weak layers that lead to catastrophic slab failures. In the Himalayas, dendrochronological studies using tree rings to reconstruct avalanche history show that avalanche frequency has increased from one major event per decade in the mid-20th century to nearly one event per year in recent decades. The avalanches are not only more frequent but larger, traveling greater distances and occurring earlier in the season. Temperatures in some parts of the Himalayas have risen by 0.2 to 0.4 degrees Celsius annually, a rate of warming that exceeds even the Arctic average. The changing seasonality of avalanches has profound implications for both human safety and ecosystem function. Winter recreationists and workers who have learned to read traditional avalanche conditions find themselves navigating hazards that don't follow the old rules. Search and rescue teams trained for specific types of avalanche conditions encounter wet slides, slush flows, and other phenomena that require different tactics and equipment. Communities that developed land use patterns based on centuries of experience with where avalanches could and couldn't reach are discovering that the hazard zones have expanded beyond historical boundaries. The invisible dangers in the snowpack. To truly understand how climate change is altering avalanche behavior, we need to look at what's happening at the microscopic level within the intricate architecture of the snowpack itself. Snow is not a simple substance, it's a dynamic, constantly changing material, and the transformations it undergoes determine whether a slope is stable or poised on the edge of catastrophic failure. When snow first falls, each flake is a crystalline work of art, with six-fold symmetry and intricate branching patterns. These stellar dendrites, plates, needles, and columns that tumble from winter clouds are masterpieces of molecular organization. Water molecules arrange themselves in hexagonal lattices, creating the infinite variety of snowflake forms that have fascinated scientists and artists for centuries. But from the moment these crystals land, they begin to change. Temperature gradients within the snowpack drive metamorphosis. Water molecules migrate from areas of higher energy to areas of lower energy, moving through the snowpack as vapor. This process, called temperature gradient metamorphism, can completely restructure the snowpack over days or weeks. Crystals round and bond together in a process called equitemperature metamorphism, forming stronger layers, or they develop into large, angular, faceted crystals with weak bonds in a process called kinetic growth metamorphism, forming treacherous layers that can fail catastrophically. The physics of snow crystal formation and metamorphism is extraordinarily complex. Each crystal's shape depends on the temperature and humidity conditions it experiences as it falls. Column crystals form at temperatures between -5 and -10 degrees Celsius. Plates develop at temperatures between -10 and -15 degrees. Dendrites, the classic branched snowflakes, grow between -12 and -16 degrees. Understanding these formation conditions helps avalanche forecasters predict what type of snow is falling and how it will behave once it lands. Once on the ground, snow undergoes constant transformation. The sharp points and delicate branches of fresh snow crystals begin to sublime, transitioning directly from solid to vapor without becoming liquid. This vapor moves through the air spaces in the snowpack, then condenses again at crystal contact points. Over time, this process rounds the crystals and grows bonds between them, transforming the loose powder into consolidated snow. The rate of this bonding process depends critically on temperature. At temperatures just below freezing, bonds grow quickly, and fresh snow can become well bonded within hours or days. At extremely cold temperatures, as are typical of the traditional Arctic climate, bonding proceeds much more slowly. A snowpack in Svalbard at -30 degrees Celsius bonds at a fraction of the rate of a snowpack in the Alps at -5 degrees. This temperature dependence has profound implications for avalanche hazard. In warmer conditions, fresh snow quickly bonds to the old surface, creating a unified, stable snowpack. But if the old surface consists of weakly bonded crystals, or if it's covered in surface hoar or ice crust, the new snow may bond poorly even if temperatures are favorable for bonding within each layer. The result is a slab of well-bonded new snow sitting on top of a weak layer that can fail catastrophically. In a traditional Arctic snowpack, cold temperatures and minimal temperature variation created relatively uniform snow layers. The extreme cold meant slow metamorphism, stable bonds, and a snowpack that might be deep but was generally predictable in its behavior. Temperature gradients existed, certainly. The ground beneath the snow is typically warmer than the surface, creating an upward flow of water vapor. But these gradients were relatively gentle and consistent. Weak layers existed in traditional Arctic snowpacks, but they were usually associated with specific weather events. Prolonged cold snaps under clear skies created surface hoar, those feathery ice crystals that form on snow surfaces when water vapor condenses directly from the air onto the cold surface. Surface hoar crystals can grow to remarkable sizes, sometimes several centimeters long, creating forests of delicate ice feathers on the snow surface. When buried by subsequent snowfall, these weak crystals create treacherous, persistent weak layers that can remain hazardous for weeks or months. Another type of weak layer in cold snowpacks is depth hoar, formed when strong temperature gradients drive rapid crystal growth deep within the snowpack. Depth hoar consists of large, faceted, cup-shaped crystals with minimal bonding between them. It has the consistency of rough sugar, and under load it can collapse suddenly, triggering avalanches. Depth hoar typically forms near the base of the snowpack where temperature gradients are strongest, and it's particularly common in continental climates with shallow, cold snowpacks. The traditional Arctic, with its deep, cold snowpack, usually didn't favor depth hoar formation except in specific circumstances like shallow snow early in the season. Climate change is fundamentally altering this microstructure in multiple ways. Increased temperature variability means more dramatic temperature gradients within the snowpack. On a day when air temperature swings from -15 degrees to 0 degrees, the temperature gradient near the snow surface becomes very steep. These steep gradients drive the formation of faceted crystals, depth hoar, and other weak layers at accelerated rates. The snowpack's internal structure becomes more layered, more complex, and more prone to containing persistent weak layers. Freeze-thaw cycles, once rare in the Arctic, are becoming common. Each cycle creates ice layers and weak interfaces that compromise the overall strength of the snowpack. When temperatures rise above freezing, even briefly, liquid water appears in the surface layers. This water percolates downward to some extent, but much of it refreezes as temperatures drop again, creating ice crusts. These crusts are hard and strong within themselves, but they create slippery interfaces where new snow bonds poorly. The formation of ice layers has cascading effects through the snowpack. Ice conducts heat more efficiently than snow, altering temperature profiles. Ice is impermeable to water, so when subsequent melt events occur, water pools on top of ice layers rather than percolating deeper. This ponding creates zones of weakness where avalanches can initiate. Ice layers also prevent snow from settling and consolidating normally, maintaining air gaps and weak zones that would otherwise heal over time. Perhaps most insidiously, ice crusts from midwinter melt events can become buried by later snowfalls, creating hidden weak layers deep within the snowpack. Unlike surface hoar, which skilled observers can sometimes detect from snowpack profiles, buried ice crusts can be very difficult to identify. They create what avalanche professionals call persistent deep slabs, avalanche conditions that can remain hazardous for entire seasons and are notoriously difficult to forecast. The changing character of Arctic precipitation itself is altering snowpack structure. When storms deposit snow at temperatures just below freezing, the snow arrives with higher moisture content and density than colder snow. This dense snow bonds more quickly, but also loads underlying layers more heavily. The combination of rapid bonding within the new snow and high loads on the old surface creates conditions where avalanches can occur very quickly after storms, sometimes while snow is still falling. When precipitation falls as rain, even briefly during a storm, it can create internal ice layers at random depths within the fresh snow. A storm might start as snow, transition to rain for an hour, then return to snow. The result is a snow layer sandwich with ice in the middle, strong snow above and below, but separated by a slippery interface where failure can initiate. The chemical composition of snow is also changing in subtle but important ways. As the Arctic warms and sea ice retreats, more open ocean is exposed. This increases the transport of sea salt aerosols into the atmosphere. Snow falling in Arctic coastal regions now contains higher concentrations of salt particles, which act as nuclei for ice crystal formation and can alter the bonding properties of snow. Industrial pollutants transported to the Arctic from lower latitudes add dust, black carbon, and other contaminants that affect snow's optical properties, changing how it absorbs and reflects solar radiation. These chemical changes influence how snow responds to sunlight. Dust and black carbon darken snow, causing it to absorb more solar radiation and melt more quickly. This can trigger earlier onset of wet avalanche conditions and alter the timing of snowmelt throughout the season. In some regions, the deposition of Saharan dust on alpine snowpacks has been shown to advance melt by several weeks. Similar processes are now occurring in the Arctic as changing atmospheric circulation patterns transport pollutants to regions that were once pristine. Climate change is fundamentally altering this microstructure. Increased temperature variability means more dramatic temperature gradients within the snowpack. These steep gradients drive the formation of depth hoar and other weak layers at accelerated rates. Freeze-thaw cycles, once rare in the Arctic, are becoming common. Each cycle creates ice layers and weak interfaces that compromise the overall strength of the snowpack. Rain-on-snow events add another layer of complexity that deserves deep examination, because these events represent perhaps the single most dangerous consequence of Arctic warming for avalanche hazard. The physics of what happens when liquid water enters a cold snowpack is complex, violent, and often counterintuitive. When rain begins falling on snow, the first effect is simple addition of mass. Rain is water, and water is heavy, about 800 times denser than fresh snow. A few millimeters of rain might seem insignificant, but when this water infiltrates a snowpack, it adds substantial weight to surface layers. This loading effect alone can be enough to trigger avalanches on slopes that were marginally stable before the rain began. But the addition of mass is just the beginning. As raindrops hit the snow surface and begin to percolate downward, they carry thermal energy. Water at 0 degrees Celsius contains far more heat energy than ice at 0 degrees because of water's high heat of fusion. This thermal energy, transferred to the snowpack, begins melting snow crystals at grain boundaries and bond points. The meticulous architecture of crystal bonds that might have taken days or weeks to develop can be destroyed in hours. The liquid water itself acts as a lubricant at layer interfaces. Snow has natural friction that helps hold it in place on slopes. This friction depends on mechanical interlocking of crystals and on adhesion at contact points. Water disrupts both mechanisms. It fills void spaces, allowing crystals to slide past each other more easily. It dissolves bonds that had been created through vapor deposition. The result is that slopes that were stable under dry snow conditions become highly unstable once water infiltrates. The path that water takes through a snowpack is not uniform. Water follows channels and preferential flow paths, moving quickly through some parts of the snowpack while barely penetrating others. These flow fingers can create localized zones of weakness that are difficult to detect, but can serve as trigger points for avalanches. A slope might have adequate strength over 99% of its area, but if a single finger of water infiltration creates a weak zone where an avalanche can initiate, the entire slope can fail. When water percolates downward through the snowpack, it eventually encounters impermeable or semi-permeable layers, ice crusts from previous melt events, dense wind slabs, or fine-grained layers that resist water transmission. At these interfaces, water accumulates, ponding horizontally. This creates layers of liquid water trapped within the snowpack. These water layers dramatically weaken the snowpack in two ways. They add huge amounts of mass exactly where it's most dangerous, loading the slope above a weak interface, and they create a frictionless surface where failure can easily initiate. The ponding of water also creates pressure within the snowpack. As water accumulates at an impermeable layer, it cannot compress or escape easily. The hydrostatic pressure builds, physically pushing layers apart and reducing the mechanical strength of the snowpack. In extreme cases, trapped water can create what amounts to an internal hydraulic pressure system that blows the snowpack apart from within. Temperature effects add further complexity. When water refreezes within the snowpack, it releases latent heat, warming the surrounding snow. This warming can weaken bonds throughout a large volume of snow, creating widespread instability. The refrozen water forms ice layers at depths, determined by the local temperature profile and the amount of water present. These ice layers then persist within the snowpack, creating weak interfaces for weeks or months. Arctic rain-on-snow events often occur under specific meteorological conditions that amplify their danger. Atmospheric rivers, long, narrow corridors of concentrated water vapor transport originating from lower latitudes, have been identified as a major mechanism delivering rain to the Arctic. These atmospheric rivers can carry astonishing amounts of moisture, sometimes equivalent to the flow of major rivers like the Mississippi, all concentrated in a band just a few hundred kilometers wide. When an atmospheric river intersects with the Arctic during winter, conditions can shift dramatically within hours. Temperatures that had been -20 degrees can rise to above freezing. Precipitation that had been falling as light, dry snow can transition to heavy rain. Wind speeds increase dramatically, both loading slopes with wind-drifted snow and eroding snow from windward aspects. The combination creates what avalanche forecasters call a perfect storm for avalanche activity. Case studies of specific rain-on-snow events reveal their destructive potential. In 2016, a major rain-on-snow event in West Greenland triggered 800 slush avalanches. 800. In a region where slush avalanches had been considered relatively rare, a single weather system produced more slides than had been documented in the previous decade. Many of these avalanches reached sizes unprecedented in the historical record, traveling distances that exceeded all previous observations. The event was triggered by an atmospheric river that transported warm, moist air from the North Atlantic to western Greenland. Temperatures rose above freezing across elevations up to 1,500 meters. Rain fell continuously for more than 24 hours. The snowpack, which had been accumulating normally throughout the winter, became supersaturated. Slopes that had been stable for months suddenly failed, sending torrents of water-laden snow cascading down valleys. The Nuuk region of Greenland experienced similar conditions, with rain-on-snow events generating significant impacts, including slush avalanches. In Iqaluit, Nunavut, Canada, another rain-on-snow event demonstrated the infrastructure vulnerabilities. Ice accumulation on roads closed transportation networks. Power lines sagged under the weight of ice accretion. Drainage systems designed for snow that melts gradually in spring were overwhelmed by sudden influxes of liquid water in midwinter. The atmospheric blocking patterns that facilitate these Arctic rain-on-snow events are themselves being influenced by climate change. Atmospheric blocking occurs when high-pressure systems become stationary. persisting for days or weeks in locations where they block the normal west to east progression of weather systems. When blocking occurs in specific configurations, it can channel warm, moist air northward into the Arctic, while simultaneously preventing cold air from flowing south. Research suggests that Arctic warming is affecting the jet stream in ways that promote more frequent and persistent blocking patterns. The mechanism involves the reduced temperature gradient between the Arctic and mid-latitudes. The jet stream is driven by temperature differences. As the Arctic warms faster than lower latitudes, this temperature gradient weakens, and the jet stream becomes wavier and slower moving. These large waves can create persistent blocking patterns that maintain unusual weather conditions for extended periods. The result is that Arctic rain-on-snow events, which were once rare anomalies, are becoming more frequent and more intense. Climate projections suggest that by mid-century, many Arctic regions will transition from snow-dominated to mixed precipitation regimes, with rain possible in any month of winter. Some coastal regions may receive predominantly rain rather than snow for much of the traditional winter season. This transition has profound implications that extend beyond avalanche hazard. Rain-on-snow events affect ice formation on rivers and lakes, altering the timing and safety of ice roads that Arctic communities depend on for winter transportation. They impact wildlife, creating ice crusts that prevent grazing animals from accessing food. They alter hydrology, sending winter runoff into rivers when ecosystems are adapted to expect it in spring. They affect permafrost thermal regimes, determining how much heat the ground loses or retains. They represent, in many ways, the transformation of Arctic winter itself, from a predictable frozen season into something far more variable and challenging. When water percolates through snow, it can refreeze at different mountain depths, creating ice layers at seemingly random locations within the snowpack. These ice layers act as slippery surfaces where failure can initiate. They also alter the insulating properties of the snow, affecting the temperature gradients, and thus the metamorphism of layers above and below. One of the most insidious effects of climate warming on Arctic snowpacks is the increased occurrence of midwinter melt events. In the traditional Arctic climate, once snow fell, it stayed frozen until spring. But now, warm spells can occur at any time during the winter, causing partial melting and refreezing. Each of these events creates a melt-freeze crust, a hard layer within the snowpack that acts as a weak interface. When new snow falls on top of these crusts, the bond is often poor, creating conditions for slab avalanches. One of the most insidious effects of climate warming on Arctic snowpacks is the increased occurrence of midwinter melt events that would have been virtually impossible in the colder climate of the past. In the traditional Arctic climate, once snow fell, it stayed frozen until spring. Winter was a season of accumulation, not melting. The sun, when it appeared at all above the horizon during the long polar night, was too weak to generate significant melting. Air temperatures remained solidly below freezing for months on end. But now, warm spells can occur at any time during the winter, causing partial melting and refreezing. These events are becoming not just more frequent, but also more intense and longer lasting. A single warm spell might last several days, with temperatures remaining above freezing even at night. Each of these events creates a melt-freeze crust, a hard layer within the snowpack that acts as a weak interface. When new snow falls on top of these crusts, the bond is often poor, creating conditions for slab avalanches. The creation of melt-freeze crusts involves a fascinating and destructive physical process. When snow at the surface begins to melt, water drains downward into the snowpack, but the surface layer loses mass and becomes thinner. When temperatures drop again, the wet surface layer refreezes rapidly, but not uniformly. The water content determines the character of the resulting ice. High water content produces glassy, smooth ice crusts. Lower water content produces rough, angular crusts, with poor bonding to overlying snow. These crusts persist within the snowpack for the remainder of the winter, often until the final spring melt. They create what avalanche professionals call bed surfaces, slippery interfaces where slab avalanches can release. The danger is heightened because these bed surfaces can exist at various depths within the snowpack, creating the potential for avalanches that break through multiple layers at once, producing especially large and dangerous slides. Research in northern Norway has revealed troubling correlations between large-scale climate patterns and avalanche frequency that help explain why some winters produce many avalanches while others produce few. The Arctic Oscillation, a climate pattern characterized by differences in atmospheric pressure between the Arctic and mid-latitudes, appears to influence wind patterns and precipitation in ways that profoundly affect avalanche danger. The Arctic Oscillation has two phases, often described as positive and negative. During the positive phase, the pressure difference between the Arctic and mid-latitudes is greater than average. This strengthens the polar vortex, the belt of strong winds that circulates around the Arctic, effectively containing cold air in polar regions. The jet stream remains relatively zonal, flowing in a tight circle around the pole. This pattern tends to keep Arctic air in the Arctic and prevents warm air from penetrating northward. During the negative phase, the pressure difference weakens. The polar vortex becomes looser and wavier. Cold Arctic air can spill southward into mid-latitudes, while warm air from lower latitudes can surge northward into the Arctic. This phase is associated with greater temperature variability, more extreme weather events, and conditions that can load Arctic slopes with both snow and rain. When the Arctic Oscillation is in certain phases, storms track further north, bringing more precipitation and higher winds to Arctic regions. These are precisely the conditions that load slopes and trigger avalanches. Statistical analysis of avalanche records in northern Norway shows strong correlations with the Arctic Oscillation Index, particularly during winter months. Years with many avalanches tend to coincide with specific patterns in the AO, suggesting some degree of predictability. However, this correlation has been deteriorating in recent years, becoming weaker and less reliable. The reason appears to be that climate change is affecting the Arctic Oscillation itself. The pattern is becoming more variable, less predictable, and its influence on regional weather is changing. This loss of correlation is troubling because it suggests that even the large-scale climate patterns that once provided some predictability for avalanche forecasting are becoming unreliable as the climate system shifts into new regimes. Other teleconnections, large-scale climate patterns that link distant regions of Earth, are also playing roles in Arctic avalanche activity. The Pacific Decadal Oscillation, a long-term climate pattern in the North Pacific Ocean, influences storm tracks and precipitation patterns across Alaska and western Canada. El Niño and La Niña, the phases of the El Niño Southern Oscillation, affect atmospheric circulation globally, including in the Arctic. When these patterns align in particular ways, they can create conditions especially favorable for avalanche activity. For instance, certain combinations of La Niña conditions in the tropical Pacific and negative phases of the Arctic Oscillation have been linked to particularly active avalanche years in parts of Alaska. The La Niña shifts storm tracks northward, while the negative AO allows warm, moist air to penetrate the Arctic. Together, these patterns can produce the intense storms with mixed rain and snow that are most dangerous for avalanche formation. What makes this particularly concerning is that climate change appears to be affecting all of these large-scale patterns simultaneously. The Arctic Oscillation is becoming more variable. The Pacific Decadal Oscillation may be shifting toward different preferred states. El Niño and La Niña patterns are being altered by warming ocean temperatures. The jet stream, which steers weather systems, and mediates many of these teleconnections, is becoming wavier and slower moving. The slowing and waving of the jet stream deserves particular attention because it's creating weather patterns that persist for much longer than they used to. In the past, a storm system might move through in a day or two, depositing its snow or rain and then departing. Now, weather patterns can become stuck in place for a week or more. A storm that lingers for days can deposit enormous quantities of precipitation, loading slopes far beyond anything in the historical record. Similarly, warm spells that in the past might have lasted a day, enough to create some surface melting but not fundamentally alter the snowpack, now persist for several days. This extended warming allows melt-freeze crusts to develop through greater depths of the snowpack, creating more extensive weak layers. The cumulative effect of these longer-lasting weather events is to create snowpack conditions that are more complex, more layered, and more prone to catastrophic failure than anything experienced in the traditional Arctic climate. Wind patterns are also changing in ways that affect avalanche formation. Wind is crucial for avalanche development because it transports snow from windward to leeward slopes, creating dense wind slabs that can fail catastrophically. In the traditional Arctic, wind patterns were relatively consistent and predictable. Certain slopes were known to be wind-loaded and dangerous, while others were relatively safe. But changing atmospheric circulation is altering these patterns. Storms are approaching from different directions. Wind speeds during storms are increasing as a warmer atmosphere carries more energy. The result is that wind loading is occurring on slopes that historically didn't experience it, while slopes that were known to be dangerous may be experiencing less loading. This redistribution of snow by wind is complicating avalanche forecasting and hazard assessment. The increasing storminess of the Arctic also means more frequent and intense snowfall events. While overall snow accumulation may be decreasing at lower elevations as more precipitation falls as rain, individual snowstorms at high elevations are becoming more intense. A warmer atmosphere can hold more moisture, about 7% more for each degree Celsius of warming. When this moisture-laden air rises over mountains and cools, it dumps larger quantities of snow in shorter periods. These intense snowfall events create their own avalanche hazards. When large amounts of snow accumulate quickly, there's insufficient time for bonding and consolidation. The new snow piles up faster than it can stabilize, creating conditions where avalanches can occur while snow is still falling or immediately after a storm ends. These storm snow avalanches can be particularly dangerous because they occur when visibility is poor, rescue is difficult, and forecasters may not yet have assessed the full extent of the loading that has occurred. What is clear is that the large-scale climate patterns that govern Arctic weather are in flux, responding to rapid warming in ways that climate scientists are still working to understand fully. The predictability that avalanche forecasters could once rely on, knowing that certain weather patterns meant certain types of avalanche conditions, is eroding. Every winter brings surprises, new combinations of conditions, avalanches that occur where and when they shouldn't, according to historical experience. This loss of predictability is perhaps the most challenging aspect of adapting to climate change in avalanche terrain. Humans are pattern recognition machines. We learn from experience, build mental models, develop intuitions about risk. But when the patterns themselves are changing, when experience becomes an unreliable guide, we're forced to operate with much higher levels of uncertainty. The Longyearbyen avalanches are stark demonstrations of this uncomfortable reality. Even after experiencing one deadly avalanche, implementing state-of-the-art warning systems, and taking extensive protective measures, the community was still unable to prevent a second major avalanche just 14 months later. What makes this particularly concerning is that climate change appears to be affecting these large-scale patterns. The Arctic Oscillation is becoming more variable and less predictable. The jet stream, which steers weather systems, is becoming wavier and slower moving, leading to weather patterns that persist for longer periods. A storm that might have passed through in a day or two now lingers for a week, dropping enormous quantities of snow or rain, or both. Ecosystems under pressure. While human safety concerns rightfully dominate discussions of increased avalanche activity, the ecological consequences of changing avalanche patterns deserve attention as well. Avalanches are not merely destructive forces, they're also agents of ecological creation, landscape architects that shape habitat, redistribute nutrients, and create the patchwork of vegetation that characterizes avalanche-prone regions. Traditional avalanche paths through forested terrain create open corridors that support plant communities dramatically different from the surrounding forest. These avalanche chutes become havens for berries, wildflowers, and the animals that depend on them. Grizzly bears in Montana, for example, rely heavily on huckleberries that grow abundantly in avalanche paths. The periodic disturbance from avalanches prevents forest encroachment, maintaining these productive openings generation after generation. Climate change is disrupting these ecological patterns in complex ways. In some regions, decreased avalanche activity at lower elevations is allowing forests to encroach on formerly active avalanche paths. In other areas, increased avalanche activity is expanding the area of disturbance, creating new openings, but also destroying mature forest that might not recover. The timing of avalanches matters too. Early season avalanches can destroy nesting sites. Late season slides can wipe out newly emerged vegetation before it sets seed. For Arctic wildlife, the consequences of changing avalanche patterns intersect with other climate impacts in compounding ways. The formation of ice crusts from rain-on-snow events creates barriers that prevent caribou, reindeer, and muskoxen from accessing the vegetation beneath the snow. These animals have evolved to dig through deep snow to reach the lichens and plants that sustain them through winter, but they cannot break through solid ice. The consequences can be catastrophic. In the winter of 2021, approximately 80,000 reindeer starved to death in northern Russia when a thick ice layer coated the Yamal tundra following a major rain-on-snow event. This wasn't an isolated incident. In 2013, over 60,000 reindeer died in the same region under similar circumstances. Indigenous peoples who depend on reindeer herding for their livelihoods watched helplessly as their herds perished, unable to reach food that lay just centimeters beneath an impenetrable ice crust. These die-offs have cascading effects through Arctic food webs. Predators like wolves and wolverines lose their primary prey. Scavengers feast briefly and then face hunger. The decomposing carcasses release nutrients in pulses that alter soil chemistry and plant growth. Human communities that depend on hunting or herding face food insecurity and economic hardship. The vocabulary that indigenous Arctic peoples developed over millennia for different types of snow and ice includes terms for conditions that promote or prevent grazing, that support travel or make it dangerous, that indicate stability or warn of hidden hazards. This traditional ecological knowledge represents a vast database of observations accumulated across countless generations. But climate change is introducing conditions that these knowledge systems never encountered. New types of ice layers, unfamiliar temperature regimes, unprecedented precipitation patterns, all of these challenges threaten to overwhelm the adaptive capacity of both human communities and the animals they depend upon. The engineering challenge. As Arctic communities grapple with increasing avalanche hazards, engineers face a daunting challenge. How do you protect settlements from hazards that are rapidly evolving and fundamentally unpredictable? Traditional avalanche protection in places like Switzerland and Austria relies on a sophisticated toolkit of structural measures developed over more than a century. Snow fences prevent accumulation in starting zones by disrupting wind patterns and holding snow in place. Deflection dams redirect avalanches away from infrastructure, channeling them into safe runout zones. Catchment basins dissipate avalanche energy through impact with carefully engineered obstacles. Tunnels or galleries allow avalanches to pass harmlessly over critical infrastructure like roads and railways. These engineering solutions represent the accumulated wisdom of generations. They're expensive, requiring detailed hazard analysis, careful site-specific design, and robust construction to withstand the enormous forces involved. A single avalanche protection project can cost millions or tens of millions of dollars, but they work, at least in temperate mountain environments where avalanche behavior is relatively well understood and historical data provides a reliable basis for design parameters. The economics of avalanche protection involve complex cost-benefit calculations. How much is it worth to protect a road that might be hit by an avalanche once every 20 years? How do you value human lives that might be saved versus the certain costs of construction? In established mountain communities with long historical records, these calculations can be made with reasonable confidence. In the Alps, for instance, engineers can estimate with some reliability that a particular avalanche path has a 100-year return period for a certain size avalanche, and they can design protection accordingly. But the economics become far more challenging when the future is uncertain. If climate change is increasing avalanche frequency, what was once a 100-year event might now be a 50-year or 20-year event. If avalanches are traveling further than historical records suggest, protection structures designed for the past may be inadequate for the future. And if the rate of change is rapid, structures built today might become obsolete within decades. In the Arctic, however, everything is more difficult, both technically and economically. First, there's the basic challenge of Arctic construction. Building anything in permafrost regions requires specialized techniques that add substantial cost and complexity. Foundations must account for ground that expands and contracts with freeze-thaw cycles. Concrete won't properly cure in extreme cold, so it must be heated during placement and curing. Steel becomes brittle at very low temperatures, requiring special alloys or heat treatment. Equipment must be winterized to operate in conditions that would destroy standard machinery. The short construction season adds further constraints and costs. In many Arctic locations, construction can only occur during a few months of summer when ground conditions allow heavy equipment access. This compressed schedule means mobilizing large crews and equipment for short periods, driving up labor costs. Materials must be stockpiled in advance, as transportation may be impossible during winter. Any delays can push projects into the following year, multiplying costs and leaving communities vulnerable in the interim. Labor costs in remote Arctic locations are typically 2 to 5 times higher than in more accessible areas. Skilled workers must be flown in and housed, often in temporary facilities that themselves must be constructed and heated. The harsh working conditions, isolation, and danger mean higher wages and more extensive support infrastructure. A project that might employ 20 workers in a temperate location might require 50 in the Arctic, accounting for the less efficient working conditions and the need for more extensive safety precautions. Material costs are similarly inflated. Everything from concrete and steel to fasteners and fuel must be transported to remote sites, often by air or sea, followed by overland transport on ice roads or by tracked vehicles. The carbon footprint of such projects is substantial, adding ethical considerations to the economic calculus. Is it justified to emit large quantities of greenhouse gases to protect communities from hazards that are themselves caused by greenhouse gas emissions. More fundamentally, though, there's the problem of designing for an unknown future. Traditional engineering relies heavily on the concept of return periods, estimating, for example, that an avalanche of a certain size has a 1 in 100-year probability of occurring. These estimates are based on historical records and assume that the past is a reasonable guide to the future. Engineers design structures to withstand forces associated with specific return periods, balancing safety against cost. But in a rapidly changing climate, this fundamental assumption breaks down. The 100-year avalanche of the past might become the 50-year avalanche of the future, or the 10-year avalanche. Or conversely, what appears to be a 10-year event based on recent experience might actually be a 100-year event that just happens to have occurred several times in a brief period of unusual conditions. The statistical foundation of risk assessment crumbles when the underlying climate regime is in flux. The avalanches that hit Longyearbyen in 2015 and 2017 both exceeded what hazard models predicted as extreme events. The protective measures installed after the first avalanche proved insufficient to prevent the second. This isn't simply a failure of engineering or of the specific designs chosen. It represents a fundamental challenge of designing for a non-stationary future, where the statistics that underpin risk assessment are constantly shifting. Consider the snow fences installed above Longyearbyen after the 2015 avalanche. These structures cost approximately 400 million Norwegian kroner, roughly $40 million US dollars. They consist of massive steel structures anchored deep into the bedrock, designed to hold snow in place and prevent avalanches from forming in the most dangerous starting zones. The engineering analysis that determined their size, spacing, and placement was based on the best available science, using sophisticated computer models and expert judgment. But those models and that expertise were calibrated against historical data from a climate that no longer exists. The snow fences were designed to handle the largest avalanches that historical records suggested were plausible. What happens when climate change produces avalanches that exceed those historical bounds? The fences might still provide some benefit, perhaps reducing avalanche frequency or magnitude, even if they can't eliminate the hazard entirely. Or they might be insufficient, failing at their primary purpose while representing an enormous investment that could have been directed elsewhere. This uncertainty bedevils every aspect of avalanche protection planning in the Arctic. Should hazard zones be drawn conservatively, assuming avalanches will travel further than ever observed? Such an approach protects lives but might render large areas unusable, constraining development and imposing economic costs. Or should hazard zones be drawn based on historical evidence, accepting that some residual risk remains? This approach allows fuller use of available land, but might leave people in harm's way. Some researchers argue that we need to abandon probabilistic approaches to avalanche hazard assessment in Arctic regions and instead adopt scenario-based planning that considers a much wider range of possible conditions. Instead of trying to estimate the probability of specific avalanche magnitudes, planners would define multiple scenarios ranging from optimistic to catastrophic and develop strategies for each. This approach acknowledges fundamental uncertainty about future conditions and seeks to build resilience across a range of possible futures. Others suggest that protective measures should be designed not for specific avalanche magnitudes, but for adaptability, with structures that can be modified or expanded as understanding of the hazards evolves. This might mean installing snow fence systems with provisions for adding additional rows or increasing their height, or it might mean building deflection dams with designs that allow for later expansion. Such adaptive approaches carry their own costs. The initial construction must anticipate future modifications, and implementing those modifications when they become necessary represents additional expense. Whatever approaches are adopted, one thing is clear: the cost of protecting Arctic communities from avalanche hazards is going to increase dramatically. The Norwegian government has already spent hundreds of millions of kroner on protective measures for Longyearbyen alone. Similar investments are being made or contemplated in other Arctic communities facing avalanche threats. Multiply this across the thousands of communities in avalanche-prone Arctic regions, and the total cost could reach into the tens or hundreds of billions of dollars. And there's no guarantee that even massive investments in protection will be sufficient. Some locations may simply become too dangerous to inhabit as climate change intensifies. Already, certain areas of Longyearbyen have been placed off limits, with houses abandoned and demolished. The economic loss from these abandoned properties, homes that people invested life savings to purchase, businesses that employed workers and served communities, represents just a fraction of the total cost, but it's a cost borne by individuals who did nothing wrong except live in the path of a changing climate. The question of who pays for avalanche protection has no easy answers. Should costs be borne locally by the communities at risk? This approach makes sense from a responsibility perspective. Communities choose to locate in avalanche terrain and arguably should bear the costs of protection. But many Arctic communities have limited tax bases and cannot afford the massive investments required. Should national governments fund protection? This spreads costs across broader populations, but raises questions about why taxpayers who chose to live in safe locations should subsidize those in dangerous areas. Or should the international community contribute, recognizing that Arctic avalanche hazards are consequences of global climate change to which all nations have contributed? This approach has equity on its side. The Arctic nations and communities bear disproportionate costs from a problem they did little to create, but international funding mechanisms for climate adaptation remain limited, and political support for large transfers to relatively wealthy Arctic nations is uncertain. Insurance presents another challenge. Traditional insurance models rely on risk being predictable and quantifiable. But if avalanche risks in the Arctic are changing rapidly and unpredictably, how can insurers price policies? The tendency is for insurance to become prohibitively expensive or unavailable entirely in high-risk areas. This creates economic hardship for homeowners and businesses, while potentially signaling through market mechanisms that certain locations are becoming uninhabitable. As more difficult decisions about managed retreat from high-hazard zones will likely become necessary, the economic and social costs multiply. Relocating communities is extraordinarily expensive. Not only must new infrastructure be built in safer locations, but the economic and social fabric of communities is disrupted. Traditional hunting and gathering grounds may no longer be accessible. Cultural and historical sites may be abandoned. The trauma of displacement, the loss of sense of place, the severing of connections to land, these are real costs, even if they don't appear in economic analyses. The experience of Alaskan native villages facing coastal erosion provides sobering precedents. Several villages, including Kivalina, Shishmaref, and Nutok, have been planning relocations for years, as erosion exacerbated by sea ice loss threatens their existence. The costs are staggering. Estimates for relocating individual villages run to hundreds of millions of dollars. The process is slow, complicated by questions of land rights, infrastructure planning, and funding. And the social and cultural costs of leaving ancestral lands are immeasurable. Could similar relocations become necessary for communities facing escalating avalanche hazards? It's a possibility that no one wants to contemplate, but that may become unavoidable if climate change continues unabated. The economic analysis becomes almost impossible in such cases. How do you quantify the value of a community's continued existence in its traditional location? How do you compare the costs of relocation against the costs of trying to provide protection that might ultimately prove insufficient? The forecast for the future. Looking ahead, every credible climate model projects continued and accelerating warming in the Arctic. The only question is how fast and how far temperatures will rise, which depends primarily on future greenhouse gas emissions. Even under relatively optimistic scenarios that assume significant emissions reductions, the Arctic is committed to additional warming over the coming decades, simply because of the greenhouse gases already in the atmosphere. What will this mean for avalanche hazards? The scientific consensus suggests several clear trends. First, the transition from snow to rain will continue to accelerate. By mid-century, many areas that currently receive primarily snow in winter will see mixed precipitation or predominantly rain. This shift will extend the season during which rain on snow events can trigger dangerous wet avalanches and slush flows. Second, the elevation of reliable winter snow cover will continue to rise. Avalanche activity at low and mid-elevations will generally decrease as snow becomes less persistent. But at high elevations, conditions are likely to become more hazardous. Storms will be more intense, depositing larger quantities of snow in single events. Temperature fluctuations will be more extreme, creating more unstable layering within the snowpack. The net result may be fewer but larger avalanches at the highest elevations. Third, permafrost degradation will continue to destabilize mountain slopes. Rock avalanches and other mass movements triggered by thawing permafrost are likely to increase in frequency and magnitude. These events pose particular dangers to infrastructure and communities because they can occur without warning and have enormous destructive power. Fourth, the season of avalanche hazard will become less predictable. In the traditional climate, avalanche danger followed a relatively clear seasonal pattern. This pattern is breaking down. Mid-winter avalanches triggered by warm spells are becoming more common. Late-season avalanches are occurring later into spring and even summer. The traditional window of safe travel and activity in avalanche terrain is narrowing or disappearing entirely in some regions. Research on specific Arctic regions provides some quantitative estimates of these changes. In northern Norway, studies suggest that slush flow frequency could increase by 40% or more as winter rainfall continues to rise. In Alaska, the number of days per winter with avalanche conditions is projected to increase at high elevations, while decreasing at lower elevations, with the crossover occurring around 1,500 to 2,000 meters. For communities, infrastructure, and industries that operate in Arctic avalanche terrain, these projections present difficult challenges. The traditional approach to avalanche hazard management, learning from history, developing experience-based rules of thumb, identifying safe and dangerous terrain based on past events, is becoming less reliable. Historical avalanche paths may become dormant while new paths activate in locations that were previously considered safe. Protective structures may prove inadequate for avalanches that exceed design parameters based on historical records. Adapting to uncertainty. In this rapidly evolving situation, how should communities, governments, and individuals respond? There are no easy answers, but several approaches show promise. First, there's an urgent need for improved monitoring and early warning systems. Real-time weather data, automated snowpack monitoring, and sophisticated modeling can provide short-term warnings that give communities time to evacuate before dangerous conditions develop. The avalanche warning system established in Svalbard after the 2015 disaster, despite its limitations, has successfully triggered evacuations that likely saved lives. Expanding such systems across Arctic regions should be a priority. Second, land use planning needs to become more conservative in assessing avalanche hazards. If historical records no longer provide reliable guides to future conditions, planners should assume larger, more frequent avalanches and wider hazard zones. This might mean restricting development in areas currently considered safe, relocating existing structures from marginal areas, or requiring more robust construction standards in avalanche-prone zones. Third, emergency response capabilities in Arctic regions need enhancement. Many Arctic communities are small, remote, and have limited local resources for dealing with major disasters. Pre-positioning emergency equipment, training local responders in avalanche rescue techniques, and establishing rapid deployment protocols for bringing in external assistance could reduce casualties when avalanches do occur. Fourth, research efforts need to intensify. We still don't fully understand how climate change is affecting avalanche formation and behavior. Expanding monitoring networks, conducting field studies, developing better physical models, and improving forecasting tools are all essential. This research needs to involve not just physical scientists, but also social scientists who can help communities adapt to changing risks, and indigenous knowledge holders whose observations and experience provide irreplaceable insights. Finally, there needs to be honest communication about residual risks. No amount of engineering or early warning can eliminate avalanche danger entirely in a rapidly changing climate. Communities and individuals need to understand that some level of risk is unavoidable, and that living in or traveling through avalanche terrain requires accepting this risk and taking personal responsibility for safety. This last point is particularly important for the growing Arctic tourism industry. Svalbard alone hosts tens of thousands of tourists annually, many of them eager to experience Arctic landscapes via snowmobile, dog sled, or on foot. Tour operators and individual visitors need to understand that the moderate avalanche danger levels they might be accustomed to from alpine ski resorts represent real and potentially lethal hazards in the Arctic, where conditions can change rapidly and rescue is difficult. The canary in the coal mine. Arctic avalanches represent more than just a regional hazard. They're a visible manifestation of how rapidly climate change is transforming the planet's most vulnerable regions. The Arctic is often called the canary in the coal mine for global warming, an early warning system showing us what's coming for the rest of the world. The changes in avalanche behavior we're witnessing in places like Svalbard and Alaska today preview the changes that will eventually arrive in temperate mountain regions as warming continues. Already, researchers in the Alps, the Rockies, and other mid-latitude mountain ranges are documenting shifts toward wetter avalanches, earlier season hazards, and more unpredictable conditions. The patterns emerging in the Arctic, increased rain-on-snow events, altered snowpack structure, shifting hazard zones, are beginning to appear at lower latitudes. The hard lessons being learned in Arctic communities about the limitations of historical data and experience-based hazard assessment will need to be applied globally in the coming decades. There's also a broader lesson here about adaptation to climate change. The story of Arctic avalanches demonstrates that adaptation isn't simply a matter of making incremental adjustments to existing systems. When the fundamental parameters of a system change, when rain falls where only snow should fall, when mountains held stable for millennia begin to come apart, when the past becomes an unreliable guide to the future, adaptation requires a wholesale rethinking of how we assess risks, make decisions, and plan for the future. The communities of the Arctic are learning this lesson in real time, often at tremendous cost. The 2 people who died in Longyearbyen in 2015, the thousands of reindeer that starved on the Russian tundra, the homes destroyed and lives disrupted by avalanches that shouldn't have occurred, according to all previous understanding. These are the harsh tutors teaching us that the climate system we've known throughout human history is giving way to something new, less predictable, and potentially far more dangerous. Between ice and fire, we find ourselves then at a pivotal moment. The Arctic as it existed for the 10,000 years of human civilization, relatively stable, extremely cold, covered in reliable snow and ice, is disappearing. What's replacing it is more variable, more violent in its weather, more prone to extremes. The avalanches cascading down Arctic mountainsides are symptoms of this transformation, visible manifestations of forces that are reshaping the entire Earth system. The question facing humanity isn't whether the Arctic will continue to change. That change is now inevitable, locked in by greenhouse gases already in the atmosphere and the inertia of the climate system. The question is how fast and how far the changes will go, which depends entirely on the choices we make about future emissions. If we continue on our current trajectory of high emissions, climate models project that the Arctic could warm by 5 to 7 degrees Celsius or more by the end of this century. Under such conditions, the Arctic as we know it would cease to exist. Year-round sea ice would disappear. Permafrost would thaw to great depths. The very concept of Arctic climate would become obsolete. Even under more moderate emission scenarios, substantial changes are unavoidable. The avalanche hazards we're seeing emerge today will intensify. More communities will face difficult decisions about whether to invest in expensive protective measures or relocate entirely. More lives will be at risk. More ecosystems will be disrupted. But there's still room for hope and agency. Every fraction of a degree of warming we can prevent, every ton of greenhouse gases we can keep out of the atmosphere, translates directly into reduced hazards and impacts. The difference between 2 degrees and 3 degrees of warming might seem academic, but for a community in the path of an avalanche, for a reindeer herd trying to survive the winter, for an ecosystem hanging on at the margins of viability, that 1 degree could be the difference between adaptation and catastrophe. The story of Arctic avalanches is still being written. Its ending hasn't been determined. The choices we make in the coming years about energy systems, land use, consumption patterns, and climate policy will shape whether that ending is one of successful adaptation and resilience or of displacement, loss, and tragedy. A different kind of storm. On a recent winter day in Longyearbyen, the weather forecast called for what would have seemed impossible just a generation ago: thunderstorms. In the high Arctic, in winter, the longest thunderstorm in Arctic observation history had recently occurred in Siberia, lasting nearly an hour, twice as long as typical thunderstorms further south. A few days later, a series of 3 thunderstorms passed through a part of Alaska that rarely experiences them. These aren't mere meteorological curiosities. They're signs of an atmosphere fundamentally altered, carrying more moisture, more energy, more chaos than the Arctic has experienced in human memory. And with this altered atmosphere comes snow that falls differently, rain that falls where it shouldn't, and avalanches that defy every rule written in the hard-won experience of generations. The people of the Arctic have always lived on the edge, in a harsh environment that demands respect and punishes mistakes. They've developed sophisticated survival strategies, accumulated knowledge systems, and built cultures remarkably adapted to one of Earth's most challenging environments. But the environment itself is now changing faster than adaptation can keep pace. Perhaps the most profound lesson from Arctic avalanches is this: there are limits to adaptation. There are thresholds beyond which existing knowledge, accumulated experience, and even sophisticated technology cannot provide adequate protection. When the basic rules of the game change, when rain falls in midwinter, when mountains held firm for millennia begin to crumble, when avalanches reach places they've never reached before, we enter a realm of deep uncertainty where confidence gives way to humility. The Arctic is teaching us that we've pushed the climate system beyond the boundaries of the relatively stable Holocene epoch that cradled human civilization. We're entering something different, something without historical precedent, a climate state that future generations may know simply as the Anthropocene, the age when human activity became the dominant force shaping Earth's environment. The avalanches are messengers from this future. They're speaking to us in a language of snow and ice, rock and rain, telling us that the world is changing faster than we'd imagined possible, that tipping points are being crossed, that the consequences of our emissions are written not just in abstract temperature trends and sea level projections, but in real tragedies in real communities. The mountains remember. There's a Sami saying that the mountains remember everything. For thousands of years, those memories were reliable guides. The paths avalanches took, the seasons they occurred, the signs that preceded them, all of these were recorded in the landscape, in stories, in the hard lessons learned from tragedy and near misses. But now the mountains are developing new memories, recording new patterns, and the old wisdom is becoming less certain. The mountains still remember, but what they're experiencing now is unprecedented. The snow that falls on their slopes, the ice that cements their rocks, the permafrost that anchors their soil, all of it is responding to a climate that has moved outside the envelope of the past. In this time of transformation, we must develop new wisdom while honoring the old. We must combine the observational knowledge of indigenous peoples with the analytical tools of modern science. We must balance the confidence needed to act with the humility required to acknowledge how much we don't yet understand. We must invest in protection while accepting that some hazards may exceed our capacity to prevent them. We must plan for the future while understanding that the future may look very different from what we imagine. Most fundamentally, we must recognize that the avalanches cascading down Arctic mountainsides are not isolated phenomena. They're part of a global transformation, one that connects the fate of an Arctic community facing lethal snowslides to a farmer in Bangladesh facing rising seas, to a Pacific island nation watching its home disappear beneath the waves, to a forest in the Amazon struggling with unprecedented drought, to everyone, everywhere, who will inherit the climate we're creating with every ton of carbon we release into the atmosphere. The snow that falls in the Arctic doesn't stay in the Arctic. It melts, flows to the sea, becomes part of the global ocean circulation that regulates climate for the entire planet. The permafrost thawing beneath Arctic mountains releases methane and carbon dioxide that warm the atmosphere worldwide. The jet stream patterns altered by Arctic warming influence weather thousands of miles away. The lessons learned in Longyearbyen about adapting to rapidly changing hazards will need to be applied in mountain communities across the globe. We're all downslope from the changes occurring in the Arctic. The avalanche, in a sense, has already started. The question is whether we have the wisdom, the courage, and the collective will to step aside from its path before the full force of climate change crashes into human civilization with the same devastating power as a slush avalanche striking an unprepared community. The mountains of the Arctic are speaking to us. They're telling us that time is running out, that the stable climate we've taken for granted throughout history is giving way to something far more dangerous, that the choices we make today will echo through centuries. We would do well to listen. If you've found this exploration of Arctic avalanches and climate change thought-provoking, please consider liking this video and subscribing to DREAMLAB Knowledge for more deep dives into the fascinating, complex, and often unsettling realities of our changing planet. Your support helps us continue bringing you these stories that matter, these glimpses into the extraordinary transformations occurring in Earth's most extreme environments, and these reminders that we're all connected to even the most remote corners of our shared world. Sleep well, and may your dreams be as stable as Arctic snow once was.